Got it. Okay, by the way, Jane, during your talk, would you like to have people try to raise questions through the microphone, or would you rather wait till the end?
Probably waiting to the end might be the best idea.
Okay, sounds great. So we'll collect them, and then at the end of the talk, we'll have both the ones from the YouTube stream and the ones from the Zoom chat here.
Okay.
And one of us will unmute ourselves and ask them.
Sounds good.
Okay, so I think most of the people on time are getting in now. I'll start introduction. Hello, everybody. I'm Zach. Welcome to the second seminar talk of our UW seminar series hosted by the Coots Group and Brunton Group. Thank you all for joining so early in the morning here. Our speaker today is Jane Bay from Caltech. Jane Bay is an assistant professor of aerospace at the Graduate Aerospace Laboratories at Caltech. She received her PhD in computational and mathematical engineering from Stanford University in 2018. She was a postdoctoral fellow in the Graduate Aerospace Laboratories at Caltech and the Institute for Applied Computational Science at Harvard University before joining the faculty at Caltech. Her main research focuses on computational fluid mechanics, and in particular on modeling and control of wall-bounded turbulence. And she'll be giving her talk, Wall Models of Turbulent Flows via Scientific Multi-Agent Reinforcement Learning. So thank you very much, and you can take it away, Jane.
Thanks. Thank you for the introduction, and thank you for the opportunity to give a talk here. I'm very honored. So like Zach mentioned, I'll be talking about wall models of turbulent flows via scientific multi-agent reinforcement learning. And before I go into the details, I would first like to thank the Air Force MIRI grant for funding this research, and also Petros Komosakis, who was my postdoctoral advisor at Harvard, who basically made this research possible. So turbulence, probably most of you are familiar with some form of turbulence, and the most popular form of turbulence is airplane turbulence, where basically you're on a plane and then suddenly you fear for your life for the few seconds where the airplane is moving around. And the turbulence that I'm talking about is somehow related to airplane turbulence, but more generally I can define it as chaotic and disorganized motion of a fluid. So basically when an airplane experiences turbulence, it's going through a patch of turbulent air. Turbulence can be characterized by this non-dimensional number RE, which we call Reynolds number. And that's a number that is basically a velocity scale times a length scale divided by the viscosity of the fluid. And whenever this number is very large, on the order of hundreds to thousands, you get turbulent flow. So below that, you'll get laminar flow. And then once you pass that threshold, you will get turbulent flow. You could think of this non-dimensional number as also a large scale over a small scale. So when you have high Reynolds number turbulent flow, that means you have a very large scale separation between the large scales and the small scales. And turbulence is quite ubiquitous. So you'll see turbulence in pipe flow when you're moving oil through a pipe, for example, in aerodynamics. So airplanes, particularly along the wing body, you would see a lot of turbulence. Atmospheric flows, like I mentioned, is turbulent. It has a very high Reynolds number. And even some biological flows. So for example, when your heart is pumping blood, that flow could become turbulent. Turbulence research is quite important just because if you look at the data, 25% of the energy used by the industry is spent in moving fluids from one location to another or sending objects through fluids. And 25% of that energy is dissipated close to the wall. So that's why I'm interested in studying wall-bounded turbulence. And wall-bounded turbulence is responsible for 5% of the CO2 dumped into the atmosphere. So from a practical standpoint, understanding turbulence and figuring out how to first like model it and then control it is quite important. On top of that, Richard Feynman famously mentioned that turbulence is the most important unsolved problem of classical physics. So just from a scientific point of view, turbulence is a very important problem. And I mentioned wall-bounded turbulence. So wall-bounded turbulence is turbulence that happens due to a solid boundary that we call walls. So you could think of a pipe wall being a solid boundary. An aircraft wing could also be, or the body could be a solid boundary. In the atmospheric flows, the Earth's surface acts as a solid boundary, for example, and biological flows, you still have not so solid, but still a non-penetrable boundary condition. So we call flows over these rigid surfaces wall-bounded turbulence. And it's a very active research topic in turbulence. So let's talk a little bit about the current standing of simulation of high Reynolds number wall-bounded flows. So here I have one example, which is a flow over an aircraft wing. And you can see all the very chaotic and disorganized motions of the fluid on top of the airplane wing. And here I have a plot of basically the highest Reynolds number direct numerical simulation. So these are cases where we resolve all scales of motion as a function of ear. And on top of that, we have basically how our computing power has evolved throughout the years. So each of these gray dots indicate the fastest supercomputer at any given year. You can see it has kind of an exponential growth. So the y-axis is exponential in a log scale. So basically this is what we call Moore's law. So these are flops per second for these fastest supercomputers. Using a linear fit of these lines, you can estimate where basically a 1 minute simulation might lie. So this is that dark blue line. Multiply that by 8 hours and you get kind of an overnight simulation. Multiply that by 3 months and you get this light blue line where it indicates how many flops we can do using 3 months of the fastest supercomputer. So this is just like a guideline to where basically our computational strength holds as a function of year, which, you know, it has grown exponentially. So it's growing fast. So compared to that, this simulation right here, which has a Reynolds number of 180, this is a barely turbulent flow. This was done in the 1980s, and you can see that it lies somewhere between this overnight and 3 months line. Obviously, this simulation didn't take up the full fastest supercomputer, so it took longer than an overnight simulation. But you can see where kind of our state-of-the-art high Reynolds number flow lies. So more recently, we've had 2,000, our Reynolds number of 2,000 and about 5,000, and they all kind of lie between this overnight and 3 month simulation. Now, this airplane wing that you see here has a Reynolds number that's about 100,000 or above. And if you look at how this trend has been moving, you'll see that this Reynolds number of about 10 to the 5 lies way off the charts, even off this slide even. And it would be about 100 years until we can actually simulate this using direct numerical simulation, if we assume that the computing powers will continue to grow exponentially. And the reason behind the simulations being so expensive is, again, because of that scale separation that I mentioned earlier. So in a wall-bounded flow, the large scales, which I'm plotting here as the red line, which is given by the shear length scale, and the small scales, which I'm plotting here as the black line. So this is the dissipation length scale or the Kolmogorov length scale. They grow as away from the wall. So as you move away from the wall, your large scale gets larger and your small scale also gets larger, but at a very slow rate. And you'll see that as you get away from the wall, you have this very large scale separation, which in a computation, if you want to resolve all the scales, your domain has to be large enough to capture the large scales, but also your mesh has to be small enough to capture the small scale. So that's where kind of the cost related to Reynolds number comes in. So when we talk about direct numerical simulation, The cost of our simulation depends on Reynolds number as a power of 2.6. And that's where all that high cost comes from. So using DNS, it's not practical and even infeasible to run simulations of such high Reynolds numbers that are practical in engineering applications. So one idea to kind of reduce that cost is when we have this large scale separation between the large scales and the small scales, we can try to model the effect of the small scales on the large scales. And that allows us to kind of forego resolving all the scales, and we only have to resolve the large scales of the flow. And this is what we call large-eddy simulation. And by doing large-eddy simulation, here we're going to call it well-resolved large-eddy simulation, you can get a grid that looks like this, where you have fine scales close to the wall, and then away from the wall, you can go get coarser and coarser. And by doing this, you can reduce the cost of the simulation to Reynolds number to about power of 2, which is much better than the DNS, but still prohibitive in terms of using LES as a modeling tool for design, for example. For design, you would want a turnover time of on the order of days, not months or weeks, months or years, sorry. So then the next step of modeling is actually happens close to the wall. So you might have noticed that close to the wall, LES still retains that very fine grid. And that's because close to the wall, even the large scales are quite small in turbulent flows. So in order for you to be able to reproduce the physics of the near wall region, you still have to resolve very finely the near wall part. So the idea of wall modeling, which is what I'm going to talk about today, is to somehow model this near wall region so that you don't have to resolve even this part. So by doing that, your grid for WallModelLS would look something like this, where you have a very coarse grid everywhere. And the dependency on Reynolds number would be either constant or at most linear, which makes it much more feasible. So this picture here is from a WallModelLS simulation of an aircraft flight. And this could probably take on the order of like a couple of days to run the simulation. So I mentioned WallModelLS, so I'll describe a little bit more on how it actually works. So it starts with a core simulation grid. So this is a WallModelLS grid. And the idea is you take velocity and fluid information from an off-wall location, and you feed it to a wall model. And this information could be something like the wall parallel velocities, the velocity gradients, the viscosity of the fluid, and so on. And then the wall model takes that information and outputs a wall shear stress, which is then applied to the simulation as kind of a boundary condition. So the idea behind this is that instead of resolving the near wall physics to obtain the wall shear stress directly, we're going to bypass that near wall physics and supply the wall shear stress through a wall model that is capable of estimating this wall shear stress through that velocity and fluid information. So that's how WallModelLS works. Excuse me. So the current state-of-the-art wall models are mainly based on the idea that there is this universal velocity profile near the wall. So this is true for a flat plate boundary layer with zero pressure gradients, and people have studied this for a long, long time. So there's a viscous sublayer where you have the velocity being equal to the distance to the wall, and then a transition layer. And then in the log layer, you see this log law where the velocity is proportional to log of the distance away from the wall. And these constants kappa and b for this flat plate zero pressure gradient case has been empirically derived through experiments and is now considered more or less a constant these days. So the algebraic wall model, which was one of the first wall models that were used in the 70s, basically assumes that this log law is true everywhere. And by taking the velocity information off the wall, it can predict the correct wall stress that basically places the velocity on this log law. So that's how the algebraic wall model works. Now you can see that in the viscous sublayer. So for example, if your grid point that where you take the information from is not in the log layer, but in the viscous sublayer, you might encounter some errors by using this algebraic wall model. So the RANS-based wall models, which is called the equilibrium wall model in this case, basically takes that and instead of just saying that the log law is true everywhere, it has some sort of damping on that log law so that you get this viscous sublayer as well. So the idea is kind of similar to an algebraic wall model, but including the viscous sublayer as well. And you can do that by solving this ODE, and that gives you this velocity profile. One thing to note about both the algebraic wall model and the RANS wall model is that the wall models itself can contain kappa and b. So here you have kappa and b, and in the RANS wall model, you can see here that there is a kappa here, and this constant a, which relates to our intercept constant b. So basically, the wall model knows for a fact that this is the universal velocity profile. Now, the problem occurs because not all flows flow over a flat plate with zero pressure gradient. So for example, if we look at an adverse pressure gradient flow, so this happens, for example, when you have a curvature like this, a concave curve, and there's some adverse pressure gradient effects due to that curvature. So here, if you look at the mean velocity profiles, you can see for the zero adverse pressure gradient case, it matches the log law quite well. But then as you start increasing your adverse pressure gradient effect, you see that the velocity profile deviates from our known log law, so our known values of kappa and b. So there is some sort of log law. So there is this like linear region in this plot, but it is not the log law that for the flat plate boundary layer. So we would need a different value of kappa and a different value of b for each of these cases. So for the traditional wall models, you would need to recalibrate your wall model for each value of the pressure gradient, which is counterintuitive of why we're using wall models. We're using wall models to be able to predict flow, not to be able to recreate flow that we already know about. So this is the main shortcoming of the state-of-the-art wall models. Same thing for rough walls. So for example, if you have a rough wall instead of a very smooth wall, you would see discrepancies in the log law. So as you start increasing your roughness, you would see the velocity profile shifting down, which means there's a change in our intercept constant b. But if we use the current wall models, this wouldn't be captured. Now there's a different type of wall model called the dynamic wall model, which I worked on during my PhD years, where instead of assuming knowledge about these constants kappa and b, we use kind of the information from the LES field itself. So we have the LES velocity field and then a test filtered velocity field, and we somehow compare that to obtain a wall shear stress. So the benefit of this model is that it had no dependency on the log law coefficients, but it happened to be dependent on the numerics of the code, subgrid scale models, and so on, which made the model not very extendable to different types of codes. So in this study, what I did was I reformulated the WallModelLS problem as sort of a reinforcement learning problem. So here we have this picture that I showed you earlier, where we had the coarse simulation grid. We take information off the wall, feed it to the wall model, and then get wall shear stress from the wall model and apply it as a boundary condition. So if you think about it, this diagram already looks very similar to the diagram that we see in a reinforcement learning. So the coarse simulation grid can be thought of as our environment. The wall model is our agent, and the information that we're taking from the simulation to the wall model are our states. And our rewards are also calculated using some information from the simulation. And then the wall model or the agent spits back an action that can be applied as the wall shear stress. So in reinforcement learning, the objective is to find an optimal policy that maximizes the expected utility or long-term reward. So that's what we are going to try to do. So going back to kind of the more traditional diagram for reinforcement learning. So we have the environment, we have the agent, and basically we calculate the reward and state from the environment at time t. So S is going to be our state, R is going to be our reward at time t, and the agent basically spits back the action at time t, which is denoted by AT. And then the environment reacts to this action and gives back the reward and state at the next time step. So this is the traditional picture you see for reinforcement learning, and you can see how that would relate to our WallModelLS problem. And again, the goal is to maximize the expected value of future rewards. So the R, summation of R from the current time step to infinity, although in reality it's not infinity, it's some batch size, given a discount factor gamma. So this is our goal. And for this, we use the Smarties package that was developed by Guido Novati in Petros's group. And so we use an off-policy gradient method called VRacer, along with a remember and forget experience replay. So this allows us to keep experiences that are close to our current policy while discarding ones that are far away. So this is kind of how we do our reinforcement learning model. So going back to our wall modeling problem. So again, our environment is going to be the core simulation grid, and our agent is going to be the wall model. So let's look at the details of what our action states and rewards are. So for the action, I chose so one obvious choice was to spit out the wall shear stress directly. But the problem with that is the wall shear stress is dependent on Reynolds number. And if you train on a certain range of Reynolds numbers, you might not be able to obtain results that are outside that region. So I wanted it to be more of a control algorithm, which is why the action A is a constant factor that will either increase or decrease the wall stress compared to the last time step. So our wall stress at the next time step is a factor A, so this is our action, times the wall shear stress at the previous time step, where A, we've bounded between 0.9 and 1.1 so that we don't have a huge jump at each time step. But basically, it allows us to control the wall shear stress so that it can go down if it's below 1 or up if it's above 1. So that was the action that we chose. For the reward, this is the functional form. Basically, it can be divided into two parts, where the first part here is it measures the improvement from the last step. So compared to our action in the previous time step, how much has our action improved, or how much has our wall shear stress improved compared to the last step. Now, if you're already close to the true solution, you can't improve anymore. So there's another term that acts as a bonus if the error is less than 1%. So this was how our reward was set up. For the states, we've tried two different models. So the first model was kind of a very basic model, a rudimentary model that takes as states as the velocity and the wall normal location. So we know that there is some sort of universal log law, at least for the flat plate case. And there is going to be a universal log law depending on other factors such as adverse pressure gradient or roughness. So we wanted to kind of learn these log law coefficients using the velocity and the wall normal location. So this was our first model. And basically, we just take an instantaneous quantity, normalize it using what our model gave us. So these are quantities that doesn't assume anything about the log law coefficient. So it has no knowledge of the kappa or the b in any of the components of our learning. So this was the first model. The second model, we tried something a bit different, which is that we knew that there is going to be some log law slope. So even if that slope is not universal, if we can learn somehow how that slope changes with adverse pressure gradient and so on, we would be able to adapt. So the idea was to compute the instantaneous log law slope and the instantaneous log law intercept using the point measurements that we did. So again, even though this looks like it's kappa and b, it doesn't have any information about the actual kappa value and the b value. And what we're doing is we were manipulating the velocity gradient, and the wall normal location so that we can obtain the instantaneous slope. So we can basically calculate what that slope is based on our wall normal gradient of the streamwise velocity and the distance to the wall. And again, we can do the same thing for the instantaneous log law intercept. So this basically is kind of a more normalized way. So instead of just saying we know what the velocity and the wall normal location is, we're going to say we know what our instantaneous log law slope and log law intercept is. And we'll see the difference between the two models in a little bit. But basically, the thing that I want to emphasize is that in these both models, Model 1 and Model 2, they do not take as input either kappa or b directly. So they only take as input the instantaneous velocity gradient, things that are available to us from the course simulation grid. So this is the major difference between the state-of-the-art wall models that I mentioned earlier that has kappa and b built into the model, and then this reinforcement learning model. So for training, we're going to train on channel flow at Reynolds number of 2,000, 4,000, and 8,000. And again, I want to mention, I guess maybe I wasn't clear before, that we're trying to train first on a flat plate case. So our next step is to move on to adverse pressure gradient cases, but here the goal is to kind of set up a framework and to see if the wall models can be developed using reinforcement learning. So we're going to use a very simple canonical case, which the previous wall models work well on, but we want to do kind of proof of concept that reinforcement learning can do similar. So we're going to train on a channel flow at RE tau of 2,000, 8,000, 4,000, and 8,000. So this is a geometry that looks like this, where you have two parallel walls and flow moving through it. The LES details, so we're going to use a subgrid scale model called AMD. The grid resolution for these cases are about 0.1 delta. So where delta is the half channel height. So this distance between the two walls are going to be 2 delta. And this grid resolution is in line with what we observe and what we expect from WallModelLS. The grid resolution would be much, much finer for either a DNS or a wall-resolved LES. And for that, we're going to use a numerics code that is a second-order finite difference in space and a third-order Runge-Kutta in time. For the reinforcement learning part, and this is where the multi-agent part of the reinforcement learning comes in, we are going to, for each computational grid that we have on the wall parallel plane away from the wall, we're going to have an agent. So each computational grid point acts as its individual agent that trains a shared policy. So we have multiple agents training one policy, which is our wall model. Yeah, for the agents in the reinforcement learning, we're going to use the Smarties library with the V-Racer and the remember and forget experience replay. Each agent is a RNN with 2 hidden layers with 120 units each, and we've used a soft sign activation function. One thing to mention here is that here the training process is directly related to a wall model LES grid. So we're running a simulation on a wall model LES grid and learning from it. So the reinforcement learning model is learning from an actual wall model LES grid. So this is vastly different from a supervised learning standpoint, where in a supervised learning standpoint, you would take data that was already available, mostly through DNS databases, and you would learn how to extract wall shear stress information from the velocity off the wall. Now, the benefit of the reinforcement learning method is that first, you don't need that vast DNS database. So it's going to be data efficient. So we're just running very small cases, which allow us to train very fast. And we don't need the database to train on. Second one is that even though DNS and LES, they share kind of the same flow statistics, there might be some discrepancies in the numerics, for example. So just because the supervised learning method learned how to predict the wall shear stress for the next time step using the velocity information from the current time step, doesn't mean that if you integrate that over time, it would produce good results. Whereas here, because it is already pre-integrated, we know that if the model converges, we can expect good results. So just an aside there, comparison with a supervised learning approach. So what do we get when we actually train this data? So one way to look at that is to look at what I call an action state map. So here we have on the x-axis the distance from the wall, and on the x-axis we have the velocity. And in the color contours, we have our actions. So the red actions indicate that the actions are above 1.05, which means we're trying to increase the wall shear stress. And the blue region indicates regions of action less than 0.95, which means we're decreasing the wall shear stress. And the immediate thing that you can notice is that they are so they're very divided. So they're clearly divided by this line here, which is actually our log law. So that means that the model has somehow learned, without being specified our kappa and b, what our log law is going to be. And basically what it does is whenever it sees a state that is above the log law, it tries to increase the wall shear stress as to push that point down towards the log law. And if it sees a point below the log law, it tries to decrease the wall shear stress as to push that point up towards the log law. So what we see here is that the control mechanism that we've devised actually works, and that the reinforcement learning model was able to figure out how to control the wall shear stress so that our states would move closer to the true log law. So this was for model 1. So for model 1, our states were U and Y, and this is our action state map. If we move to model 2, remember we were training on kind of the instantaneous log law slope and intercept. So it's a little bit more difficult to physically understand what the action state map is doing. But one thing to take away is that there is a clear division between the regions where the actions are greatly above 1, and the actions where the regions where the actions are greatly below 1. So there is a clear division, meaning that the model has a clear distinction on when to increase or when to decrease the wall shear stress. So this is a good thing. So now let's do some testing, see how the models have trained and what kind of results we can expect. So we've tested using a higher Reynolds number channel flow. So remember, we've trained on Reynolds number of 2,000, 4,000, and 8,000. And now we're testing on channel flows of Reynolds number from 5,000 all the way to 1 million. So a pretty high Reynolds number. Same LES detail. So we're using the same subgrid scale model, same grid resolution, same numerics. And the details of the reinforcement learning is the same. So we are still putting one agent per grid point along the wall parallel direction. And it's taking the policy that we've trained from our training process. So if we look at the errors in the wall shear stress, so this is what we want to look at, and this is in percent. You'll see obviously that there's one model that has a very large error as the Reynolds number increases. So here the x-axis is Reynolds number, the y-axis is error. So the open circles here are our first model, the model that we trained on using the velocity and the wall normal location. And the closed circles are the second model where we trained on the instantaneous velocity, instantaneous log law slope and the log law intercept. So you can see clearly that the first model doesn't do quite well if we start increasing the Reynolds number. And the reason behind this is quite obvious. So when we trained on the wall normal distance and velocity, what we did was we trained on a particular range of wall normal distances. So because we had a limited Reynolds number, we were training on a limited range of y plus values. Whereas if we start increasing the Reynolds number, what happens is that the trained data is here, but what we're testing, because we kept the grid resolution the same, what we're testing is way over here. So there's a discrepancy between what it trained on and what is being tested on. So that's why as we start increasing the Reynolds number, we see a larger and larger error. Because as we know, machine learning doesn't do quite well at extrapolating. It does very well at interpolating what it's seen, but it doesn't do very well in extrapolating. So one way to mitigate that is to actually refine the grid. So if we refine the grid, we can bring down this range of y plus for the testing data close to where we trained on. So these triangles here indicate when we do grid refinement. So when we refine the grid so that our observation point aligns with where we trained on, you can see that there's a vast improvement in the error. So one way around that is to basically refine the grid to make sure that where you train on and where you test on is similar. But that's not always feasible. So you can't always expect to be able to refine and make sure that your testing data aligns with your training data. So let's focus on the second model, which seems to do well even as we increase the Reynolds number. So if we zoom in, we'll see that here's the error for the second model. It does increase with Reynolds number, which could be expected in some way. But up to Reynolds number of 1 million, we see less than a 4% error, which is still decent. Here we're comparing against the RANS-based model that I explained before. So here the RANS-based models have a very low error, even at very large Reynolds numbers. But again, you have to take into account that these RANS models have built in these kappa and B constants. So they are the best case scenario. So you can't really beat these models. But the fact that these reinforcement learning models that had no knowledge of these coefficients were able to do so well is actually quite impressive. So if we look at the velocity profiles, you'll see that up to Reynolds number of 100,000, the mean velocity profile matches quite well with our log law, which is what we expect. And then for the 1 million case, there's a slight discrepancy, which accounts for that 4% error that we see here. We've also tested this on a turbulent boundary layer. So this is a spatially evolving zero pressure gradient turbulent boundary layer with RE theta between about 1,000 and 7,000. And this is basically the region where we have DNS data to compare against. And so the numerics and the details of this solver are basically identical to the channel flow case, except for the inlet boundary condition, where basically we used a Lund recycling scheme to generate the inlet boundary condition. So if we look at the friction coefficient for this case, which is basically related to the wall shear stress, you'll see that our reinforcement learning model, which are the circles, match very well with the empirical values of the friction coefficient. And there's some discrepancy in the inlet, but that might be due to the inlet boundary condition. But as you move farther away from that inlet, you can see that the match is very good. So we can expect that the model can be extended to different flow geometries, not just the channel case. So it does work for a turbulent boundary layer as well. One final thing that I wanted to mention about this model is that, and this is the mean velocity profile for the boundary layer case. So you can see that again at different streamwise locations, you still see a very good match with the log law. So one other thing that I wanted to mention about this wall model was in the RANS-based models, such as this equilibrium wall model, what happens is that there is a deterministic relationship between the velocity off the wall and the wall shear stress. So there's an equation that basically dictates that there is 100% correlation between the velocity off the wall and the wall shear stress. And this is not physical. So you can see here on the top, we have the velocity at the off-wall location. Here we have the wall shear stress. And you can see that there's a very large correlation between these two. The reinforcement learning model, because the actions are kind of like a control problem. So instead of having a deterministic relationship, it has kind of a control relationship. You can assume that there is less of a correlation. So here is the velocity off the wall for the reinforcement learning model, and here's the wall shear stress. So there's definitely some discrepancy in those two, which is actually physical. So we want discrepancy. So if we actually look at the correlation directly, so this is the correlation between the velocity off the wall and the wall shear stress, you can see that the RANS-based model has an almost 1 correlation between the two. And the reinforcement learning model has a correlation around 0.3. And this is actually the value that you obtain when you look at DNS data. So 0.3 is about what we expect from a physical flow. So on top of just the fact that we do get pretty impressive predictions of the wall shear stress, the relationship between the wall shear stress and the flow itself is more physical in our reinforcement learning model. So that was all that I wanted to kind of share with you on this research. So to conclude, basically we use multi-agent reinforcement learning to discover wall models for large-eddy simulations. This is a more data efficient way, and there's a direct coupling between the LES grid and reinforcement learning, which wouldn't be true if we were to use supervised learning. The multi-agent reinforcement learning wall models were able to predict the wall shear stress for canonical channel and turbulent boundary layer flows. And we've observed that some formulation of the state space work better than others. So, you know, it would be good to understand what are the more generalizable state compared to others. So that's something that, you know, we still have to look at. For future work, we would be learning on adverse pressure gradient cases. So right now we've only looked at the flat plate case, which, you know, compared to the current wall models, which were, you know, exactly fit to predict those cases, you know, they don't do as well. But we assume that if we move on to adverse pressure gradient cases, we would be able to do much better than the current wall models. And with that, I would like to leave up my archive paper with Petros, and, you know, I'll be happy to answer any questions that you might have. Thank you.
Thanks very much, Jane. That's a great talk. So we're happy to take some questions either from the YouTube stream or the Zoom here. I'll start off. I was interested in a lot of this. So I've seen some, your wall models use the universal law that has the matched asymptotic with the sticking condition on the wall and the log. So anyways, I was just curious about how that relates to, I think there's simple models that use stick slip conditions. So they allow a boundary condition where the velocity slips against the wall. So I was curious if you've come across those and you know if they're too simple compared to your matched asymptotics thing. Yeah, so you know, basically there are two parts of the wall model. So one is applying a boundary condition in a meaningful way from the obtained wall shear stress. So that's what you mentioned about the slip wall models and the Neumann type boundary conditions, where basically the flow is allowed to be non-zero at the wall. So that's usually what the LES does. So even in the cases that I'm mentioning, basically those are the boundary conditions that we use. But in order to obtain that wall shear stress, what we do is we solve on kind of a secondary problem, this type of ODE or the log law slope, to obtain that wall shear stress. So there's this like two different problems. So one is actually applying the wall shear stress that we've obtained from the wall model as a boundary condition, and that's where like the
slip boundary condition and the Neumann type boundary condition work. And then there's the part where we try to obtain the wall shear stress. And in the traditional wall models that I mentioned, the algebraic wall model and the Rennes-based wall model, they basically solve that ODE or equation close to the wall to obtain that wall shear stress.
Gotcha, that's perfect. That makes a lot of sense. So the whole advantage is to the big grid spacing where you can apply the boundary condition without doing the subgrid resolution.
Right.
Yeah, okay, perfect. Thanks so much. So here's a message from A. Ramapuraman. Sorry, I'm going to butcher that name, Madhavalam. He says, thank you for your nice presentation. Can you provide more detail on the reward function? How is the true value of the wall shear stress obtained? Is it obtained from an analytical wall model?
Yeah, that's a great question. So one easy way to obtain it would be like if you have a DNS already of it, you could obtain it from there. But the cool thing about the channel flow case is that, so here, this is the case that I've trained on. So the cool thing about the channel flow case is that the wall shear stress is directly related to the pressure gradient that you impose to derive the channel. So in order to make the flow move from this location to that location, we have like a pressure gradient that goes between in between, and that pressure gradient directly relates to wall shear stress. So for this training, I didn't even have to take any empirical model. It's just a known quantity based on my simulation details itself. So that's why training on the channel flow was a pretty easy way to go about it.
Great, thanks. So another question here. By the way, whenever you are tired of questions, we can wrap up and forward emails. So just let us know. From Ricardo Balin says, great talk, thanks. I have a few questions. First, for your second model, how can you compute the log law, slope, and intercept instantaneously when those are properties of the mean flow? Instantaneously, the log flow is not observed. He has several questions, so maybe I'll go one at a time. Yeah,
so yeah, that's true. So here, basically, I'm saying that I can compute the instantaneous log law slope as a du dy times y. And if you take the mean of that, that should give you the log law. But obviously, there's going to be a spread if we're looking at instantaneous values. So what I'm trying to do is basically trying to learn kind of that average behavior and try to make the control of the wall shear stress based on kind of the learned behavior on the spread of this log law slope and log law intercept that from the instantaneous quantities. So that's how it works. It's true that instantaneously the log law is not observed, but also the traditional wall models assumes that the log law holds at every instance in time. So basically, the all wall model somehow has to expect some sort of universal behavior. And in this case, what I'm doing is that I'm assuming there is like some sort of bell curve where even the instantaneous velocity profile is somehow the slope and the intercept of the instantaneous velocity profile is somehow centered around this mean value, which is given by the universal log law.
Great, thanks. So I'll go on a second question now. It says, what are your targets to define the reward function for your two models? Is it the instantaneous mean wall shear stress? If instantaneous, where did you obtain or compute those values?
Yeah, so it's the mean wall shear stress, not the instantaneous one. And like I mentioned, the mean value is for the channel cases trivially computed. And yeah.
Yeah, okay. So one more, did you try varying the height above the wall at which you compute the state, velocity, and then velocities and log law, intercept slope, those state variables?
Yeah, so when I take the, so due to the time constraint, I didn't go into too much detail about how I sample these states. But basically, when I do the training process, I do vary the locations where I take the state in. So yeah, I do vary the height.
Okay, yeah. And last one from Ricardo, on the flat plate, did you apply the same agent learned on the channel flow?
Yes, yes. So I didn't do another learning on flat plates. I used the agents that were trained on the channel flow and just applied it directly to the flat plate case.
Great. Okay. So next from Diraj says, as a follow-up on the previous question, is tau sub omega to the m the ground truth from the LES simulations? Are the agent's actions being used while training? And do you discard simulations where the agent is way off?
Yeah, so basically the tau wall model is the wall shear stress obtained from the model. So the model at any point gives a wall shear stress, and that's kind of what the tau wall model is doing. The agents, the actions are being used while training, sure, yeah, because we are advancing the time using the actions that were obtained through the agent, and that's how reinforcement learning works. So you apply the actions, and then you see how bad or how good your reward changes. And based on that information, the policy is updated. So if you're doing well, probably you want to move towards that direction, and you update the policy that way. If you're doing bad, basically that's not what you want to do, and you want to discard that. As for the last part, do you discard simulations where the agent is way off? So this is an off policy training, which means basically you can think of it kind of as like you have your current policy, and you try kind of mutations of that current policy to see what is the best direction. So all of that information is used to improve the current policy. But after that, you don't really, use that again. If that answers your question.
Okay, great. So next is from Panaki Paul. He says, thank you for the great talk. The calculation of the state space variables requires the friction velocity. How are you obtaining the friction velocity?
Yeah, so this friction velocity is obtained from the model. So it's whatever the model gives as our estimated friction velocity. So it's not the true friction velocity, it's whatever the model gives back at that instance in time.
Great, quick one. So we're almost done here, a couple more questions, and then I'll check the YouTube if we have time. Rod Hagi says, thanks for the presentation. How does the change in the grid size for high Reynolds affect the computation cost?
Yeah, so I'm assuming you're talking about this case where if we do grid refinement, we see improved results. So here in this case, what I'm doing is I'm only refining in the wall normal direction. So I'm keeping the streamwise and the spanwise grid resolution the same while just refining in the wall normal direction. So in that case, the cost would be on the order of Reynolds number to the power 1, which is in line with what we expect from WallModelLS. And then for the other cases, I keep the grid resolution constant even as I increase Reynolds number. So the cost is constant.
Great, perfect. So next is Umesh says, what is the computational cost of your learning algorithm compared to the conventional WMLES?
Yeah, so for the computational cost, you can think of it two different ways. One is to apply an already learned model. And that's extremely fast, much faster than solving an ODE at each time step, which is what the RANS-based models do. So it's just evaluating values through your weighted model, your weighted neural network. So that's extremely fast. Now the training part does take some time, but that's just a fixed cost. So I wouldn't consider that as like the cost, compared to the conventional WallModelLS. So that cost would be the equivalent of the cost of developing a wall model. So yeah.
Yeah, great. Perfect, thanks. Okay, last question so far. Anna Guseva says, thank you for the very nice talk. Could you say a couple of words about your plot showing the dependence of the slope 1/k and the intercept constant b? And she asked, is it supposed to be linear?
Well, it's supposed to be point. So the true value of kappa and b are actually like this intercept point here where you have this cross. And you see this spread because, you know, your state is never going to be exactly that point. But what we do see here is that at least there's like a clear divide between the two actions with that point in the middle, which means there's kind of this funnel that makes sure that you move towards the correct 1/kappa and b. Yeah.
Great, thanks. I think just one more question is rolling in. Pinaki Paul asks again, do you estimate the friction velocity as the square root of model minus estimated shear stress divided by density?
Yeah, that's exactly how I do it.
Great. Okay, I think that's everybody. And I don't want to exhaust you, so I would ask questions forever, but I think we can say thanks again. Great talk. Have our little Zoom clappy hands go. Thank you. So next week, again, same time, same place. So we hope to see more people again.
Yeah, thank you.
Bye.
Thanks so much for the great talk, Jane.
Thanks.